All right, yeah, so I'm going to be talking about how dependency length minimization is affected by register in Japanese and Russian, which are both flexible languages, although the way in which they are flexible is different. Um, so it's a quick overview. Sort of the main question behind this project comes out of recent corpus-based work on dependency length minimization that's found that different languages seem to minimize to different extents. So what I wanted to know is how and why the degree of dependency length minimization differs between languages, but then also between registers of the same language. And as a sort of sub-question of this, I was interested in how we can use new sources of especially informal speech data to help answer this question. You know, traditionally getting speech data is a pretty big undertaking, but thanks to the internet, there's actually a lot of data out there waiting to be looked at. So the way I'm going to do this, I've been working on this thing that I'm calling UDEP, or the YouTube Dependency Parsing Pipeline, to make a corpus of dependency parsed YouTube captions. Okay, so some quick background. So what is dependency length and what is dependency length minimization? So dependency length is just the distance in terms of the number of words or sometimes morphemes, depending on how the data set is tagged between a dependent and its head, counting the dependent itself. So for example, here we have the sentence Maya threw out the trash, and we have dependencies of say length 1 between Maya and through and out and so on, to give us a total dependency length for the sentence of 6. This is just summing all of those numbers that you see here. And so the observation that speakers often seem to try to minimize these distances has led to this hypothesis that grammars actually require dependence to be realized as closely as possible to their heads. But what I'll be talking about here, rather than like, does minimization happen? Instead, I'll be looking at how the strategies that can be used to minimize dependencies differ across languages and registers, and what the patterns of that look like. So one way that you can minimize your dependencies is through choice of word order. So these sentences here are similar to the one from the previous slide, but now we have this really long object, right? And so in the first sentence, the dependency between through and out is still just 1. But in the second, if we move out all the way to the end of the sentence, then suddenly we have a much longer dependency of length 8. And so the total dependency length of both of these sentences is also quite different. The first being much shorter than the second, and the first is also typically preferred by speakers of English. Another way that you can reduce dependency lengths is through argument drop. And so argument drop has been talked about as a feature that can reduce like the absolute length of a sentence just in terms of number of words, but I haven't seen it talk about so much in terms of dependency length minimization. But it can actually make a big difference for this too. So looking at this example here, we have 3 sentences in Japanese that are all length 11, roughly in terms of morphemes. It's important that we're looking at sentences that are all the same length here, because later on, when I get to the graphs, we'll be thinking about dependency length in terms of total sentence length. And so the way that these sentences handle their arguments are slightly different, and this has consequences for the total dependency length. So in the first sentence, we have expressed all 3 arguments. We have the short subject, a kind of longer object, and the verb, and the total dependency length is 21. In the second sentence, we have a slightly longer object here, just to make sure that our sentences are the same length, but we've dropped that subject. And by dropping the subject, we end up with a total dependency length of just 15, which is much shorter. And then in this third example, we're using a non-canonical order, which is grammatical in Japanese and present in speech. And so here, by moving the sentence to the end, we can end up with a total dependency length of 16, which is just about the same as dropping the subject entirely. So we can see that dropping something can be as good as changing word order in terms of reducing our dependency lengths. And so previous work on DLM, so Richard Futrell and colleagues did a pretty big corpus study of like 37 languages that basically showed that all languages tend to minimize their dependencies. The total dependency lengths are shorter than we'd expect if dependency lengths between constituents were just completely random. What intrigued me about this study, though, is that they found that languages like Japanese, Korean, and Turkish seem to have longer average dependency lengths than some other languages like Italian, Indonesian, and Irish. So here's what those languages looked like in that study. And we'll see a lot of graphs like this throughout the presentation. So we have sentence length here on the x-axis, and then total dependency length of the sentences here on the y-axis. And then we have these three different lines representing different baselines. So the top red line is a random baseline showing the length of sentences if you were to essentially just scramble the words in them. So completely random word order here. And then the second blue line is the observed dependency length. So that's the actual total dependency length of every sentence in the corpus. And then this bottom green line here is an optimal baseline representing what happens if you rearrange the sentence so that the distance between all the dependencies is as small as possible. And so when we're just looking at these graphs, what I want you to focus on is the distance between this top line and the blue lines, the distance between the random and observed dependencies, or pretty much equivalently the distance between the observed and optimal dependencies. And we can see that these top three languages are much closer to their optimal baselines than these bottom three languages. And so we might ask why that variation exists. It's been suggested by Futrell and colleagues based on some stuff that Hawkins and others have said that in languages like Japanese, Korean, and Turkish, which are very head final, maybe there's less overlap between forms, and so they have more freedom in their dependency lengths. There's less pressure to minimize because there's less of a processing cost. And we do see this kind of borne out in work that Zoe Liu presented earlier in the workshop and also in Natalia's work. We can also observe that in SOV languages, if all of your constructions are verb final, then our dependency lengths are just going to be a bit longer on average than in SVO languages, but then we might expect trade-offs elsewhere, which is pretty much what I'm going to be talking about. And so the other question that comes up though is the corpora that we're actually comparing here. So as many of us are aware, a lot of large corpora historically have used written language and formal registers. Of course, this is changing. We're getting more corpora of internet speech. There's like Natalia's party corpus. But we know that there are systematic differences between registers of a language. So for example, in Japanese, in casual speech, you can have non-verb final word orders. But if we're looking at writing or very formal speech, we won't see this. And so by extension, these big cross-linguistic corpus comparisons aren't necessarily comparing the same kinds of language use, which might be okay if we're looking at something very high level like do languages minimize. But if we want to understand patterns within that, then we need to be more careful about the corpora that we're comparing. So with this in mind, we can address some more fine-grained questions. So we've seen that flexible word order and argument drop can both reduce dependency lengths. And both of these strategies are available in Japanese, but in particular, casual spoken Japanese. So the questions that I had were, one, will casual spoken Japanese look different from the previous results? Like, will it minimize its dependencies more since it has these strategies available? And then second, if so, how are these different strategies playing a role in the minimization that we see? And then to sort of help interpret the Japanese data, I also wanted to look at Russian, which is a flexible SVO language, but has more limited argument drop than Japanese does. So here's a sort of quick overview of the relevant differences between Japanese and Russian for our purposes. So as I was saying, Japanese is flexible SOV, whereas Russian is flexible SVO. But of course, the ways in which they're flexible are different. You know, here we're thinking about flexibility as a gradient. And so in Japanese, writing and also formal speech will be pretty rigidly verb final. Writing, in fact, basically completely verb final. Whereas casual speech is optionally flexible. Flexibility can fulfill certain discourse things, you know, like backgrounding or clarification. Russian, in contrast, is flexible in both writing and speech. And in fact, you know, non-SVO orders are pretty common and can be better in some context or expected, like asking and answering questions. And then, so Japanese features very frequent argument drop, whereas in Russian, argument drop is more limited. So I have some numbers here, but I'm just gonna go through them sort of quickly. So in Japanese, for speech, which is here in dark blue, we have a rate of subject drop from about 37 to 74%, depending on genre. And in writing, we have rates of about 12 to 25%, depending on the genre. In contrast, in Russian, so for fiction, we have 0 to 22%. This number is coming from very dialogue-heavy fiction. Across other genres, it maybe goes to about 4% in very formal ones. This is, again, writing here. Whereas in speech, we have a range which is actually pretty similar from 3 to 24 to 32% in conversation. And so the previous DLM results for these two languages from Futrell et al. Looked like this. So we can see, again, paying attention to the difference between the random and the observed data, that although the difference is definitely not nearly as striking as in the graphs we saw earlier, Russian is seeming to minimize a bit more than Japanese. And so the Russian data here is coming entirely from written sources. And the Japanese data, as I mentioned earlier, is coming from spoken sources, but from kind of very formal situations. So like making appointments or travel arrangements. So very formalized too situations are being represented in this corpus. So my predictions based on all of this, first were that Japanese and Russian would show more minimization in the YouTube data, so this very informal speech, than in the previous data. And then that Japanese will show a greater difference in overall minimization between these two registers because of the greater availability or the greater difference in availability of argument drop and flexibility between genres for Japanese compared to Russian. And so, as I said, the way that I did this, or the way that I looked at this, was by building a corpus of YouTube captions. So YouTube has two kinds of captions. There are the auto-generated ones, which aren't great. And then there are the community-provided captions, which are overall of pretty good quality. And just as a quick aside, YouTube has been saying that they might discontinue the community captions feature this year and replace it with a paid option, which means that most channels will probably go uncaptioned from there on. So at the end of the presentation, I'll have a QR code to one of the petitions that's going around. You can sign it if you're interested. So the way I generated the corpus very briefly is identified the top YouTube channels in Japan and Russia that contain actual speaking, and then scraped the captions from those videos using Python, processed them automatically to remove just any weird things like special characters or the timestamps, but I'm also in the process of manually processing 10% of the data so it can be compared to that. And then I parsed them automatically with the Stanford NLP dependency parser. And I'll note that sort of the reason that I went with just the top YouTube channels, or the benefit of doing that, is that they have a lot of videos, one, and two, they have big audiences, so they're more likely to have captioned videos. Of course, there are some limitations to doing everything automatically like this. So the parser doesn't do super well with casual speech, especially Japanese, because of this big difference between writing and speaking. But that said, it usually gets the dependencies right enough, since we're looking at it at sort of a higher level. We're just looking at the distance. So for example, whether it correctly identifies a subject as a subject, or it thinks that that subject, since there's no particle, say, indicating part of speech, is just like an adjunct, it still correctly places a dependency between that subject and the verb. So our lengths are mostly correct. And so to calculate the dependencies, I'm not going to go into computational details, but if you have questions, feel free to ask during Q&A. So for each sentence, I calculated the total dependency length without punctuation in the same way that we saw in the examples earlier. And then I generated 10 random versions of each sentence and calculated the total dependency length of those to get the random baseline. And then I also generated the optimal arrangement of the sentence that minimizes all the dependencies and calculated the total length of that to get the optimal baseline. And these are to match the methods used in Futrell et al. 2015. So here is what those graphs look like side by side. So up top here, we have the data from my corpus, the UDEP corpus. And then on the bottom, we have the data from Futrell et al. 2015. The only big difference between my graph and Futrell's graph is that I've put the random baseline in dark gray here. Otherwise, it's the same with sentence length graphed against total dependency length. And so on just a quick visual inspection, we can see that Japanese is actually minimizing quite a bit more than what we saw earlier. And in fact, looks like it's minimizing more than Russian. But so in order to sort of have a numerical way to compare these two things, what I'll be considering, this is kind of provisional since I don't have access to Futrell et al.'s data, and I'm definitely open to suggestions on ways to analyze the data further. But what I'll be looking at is the ratio between the area between this random and observed baseline to the area between the random and optimal baselines. So essentially what we're looking at is how much we've moved from away from random, but then normalized by how much wiggle room there actually is. And I think for our purposes, that makes more sense than comparing these slopes directly. So these in the corner are the slopes of some mixed effects linear regressions for each line, which was also done in Futrell et al. But there are a lot of things that could affect what these absolute numbers look like, not just differences between the regression potentially between the two studies, but also differences in how the two data sets are just tagged by the parser. So we'll be looking at a ratio instead. Right, so this is that ratio. So it's the area here divided by the area here. And we'll be estimating this for the Futrell et al. Data set just using the slopes instead, since the intercepts are near 0. I don't have the intercept data for his, but I do have it for mine. So I'll present the exact ratio for my data and an estimate for the Futrell et al. Data. So this is what those numbers look like. In parentheses is the estimate, just for comparison for my data. So in Japanese, we have a minimization ratio of 0.689 in the UDEP corpus, so the informal speech, which is quite different from in the Futrell et al. 2015 data, which is the more formal formulaic speech. And so that ratio is 0.556. In Russian, we have a ratio in the UDEP corpus of 0.606, and then a ratio of 0.618 in the previous written data. So what we see here is that casual spoken Japanese is seeming to minimize a lot more than the formal spoken data, and also that it's minimizing a lot more than casual spoken Russian. And surprisingly, Russian is actually pretty similar across the two studies. And so I have bi-channel data as well, but just to save time, I'm going to skip past that. If you want to see it, just ask me during Q&A. And so, as I was saying before, I've also done hand corrections. The main goal of the hand corrections was to determine sentence boundaries, since the captions usually don't have punctuation or anything like that. So you don't necessarily know whether one line is a whole sentence or whether it actually combines with the next line. And I'm also been coding for use of non-canonical orders and also for argument drop. And so quickly, this is what the corrections look like. As we can see, so the growth of all baselines in absolute terms was significantly slower in the corrected data than in the automatically corrected captions, but the overall pattern is unchanged. So our minimization ratio between the two is about 0.69 in both cases. The biggest benefit is that we get more data at these higher sentence lengths. And so overall, only about 5% of the hand corrected or hand checked utterances actually used a non-canonical order. In contrast, argument drop is extremely common. The coding for this is a bit more preliminary, but we see that 76% of clauses drop at least one argument. And just for a sort of very quick comparison to Russian, I don't have data yet for Russian argument dropping in this corpus. So I'm making a little assumption that underlying references to first-person singular agents is similar across the two, but just bear with me. But if we just look at the counts of first-person singular pronouns in Japanese versus Russian, we have about 16.2% of the Russian sentences using this pronoun at least once, using ya, whereas in Japanese, only 3.36% of sentences are using one of watashi, watakushi, boku, or ore. There's a lot more options in Japanese, but yeah. So in conclusion, it looks like argument drop might be driving dependency length minimization more than flexible word order in casual spoken Japanese. But still, these strategies do work together, and it seems like together they're allowing casual spoken Japanese to minimize dependencies more than in casual spoken Russian. And so moving forward, the goals for the project are to continue the manual correction and annotation, and maybe ideally correct the dependencies and even rerun, like train a model on the spoken Japanese data so that we can get better data for that, since it has the most trouble with the spoken Japanese data. And then also to expand to more languages and registers. And then, yeah, I just want to leave you with this, that I think, as we can all agree, looking at informal speech is a really important way to complement the existing written data that we have. And in particular, online sources like YouTube, which haven't been tapped so much, can be really powerful tools for looking at these typological patterns that are hard to detect when we're only looking at formal registers and written modalities. Thank you. And there's the QR code.
Thanks, Alex. Thanks for your great talk. I have to give a full disclosure. Alex is my graduate student, so I want to make sure that I'm obviously very excited about this, but I want everyone to know that. Okay. And so this is from just 2 years into their graduate program. All right, so Luigi has a question. Luigi, why don't you go ahead and share? Yeah, go ahead.
Oh, hi. Thank you for your very interesting talk. I think that you have really pushed the parser to the limit in analyzing YouTube videos. And I was wondering if you have tried to use maybe Spacey trained with the UD models, or I don't want to go too technical here, but we are using Spacey with UD models, so I would like to hear a comments from you about.
Yeah, I mean, I actually did think about switching to Spacey because I've read that you can use it with a slightly more accurate tokenizer for Japanese, at least. But I also, I mean, yeah, maybe you would know more about this than I do, because I also remember seeing that Spacey was maybe not so accurate for, or at least in comparison, but I forget, it might have been about something specific. So, but I definitely thought of
it is not for some languages stands for sparsely superior, but there is this nice integration between Spacey and UD that's, I guess it's worth trying. Specifically because Japanese and Russian have a strong support in the UD community. So
yeah, and I think it would also be really interesting from like a more computational standpoint to see how the data looks when we use different automatic parsers. See how much the parsing itself is affecting the patterns we see, for sure. Yeah.
Okay, thank you.
Yeah.
Other questions? Either remember we can do the hand raise function, or oh yeah, there's another one. All right, Rachel, go ahead.
Thank you. Thanks for the interesting talk. I'm just trying to think through, and it may be a slightly odd question because it's midnight here and my brain isn't firing properly, but I was just thinking through the predictions you would make about argument drop. So I think you said that the argument drop has more effect in Japanese than word order. But it seems to me that those two must go together, because argument drop is going to have more of an effect if you're an SOV language, as in the example you gave, than if you're an SVO language, right? Because you're not going to get as much minimization. So presumably it's got to be the combination of word order and argument drop that are going to end up having an effect, because the word order then controls how much minimization you get from argument drop. Does that make sense? Is that right?
No, yeah, I do think that they are working together because, right, for one thing, like dropping an argument will mostly have that, like if I go, maybe it's hard for me to go back to my example, but you know, it's dropping that subject, for example, that really makes the big difference here, right? And then actually on top of that, I mean, this is something that I only noticed like a couple of days ago because I've still been working on coding more and more of the sentences, right? But so I saw an overall rate of only 5% for non-canonical orders in the overall data, but if we look at sentences that don't have any argument drop, that rate is actually much higher. It goes up to about 15% in the sentences with all constituents expressed. So yeah, so looking at that interaction, I think would be really interesting. It might be hard to get at until I have sort of more, you know, fine-grained data on it, but it's definitely something I'm thinking about.
And then it also makes you wonder what your predictions are about languages with free word order and argument drop, and you know, what would you, anyway, I won't take up all the question time, but interesting. Thanks.
Thank you.
So that relates to a question that was asked in the Q&A section, which is, do you expect Japanese still has less DLM than Russian if you exclude all the sentences with argument drop in both languages? And so it seems like your answer might, anyway, but I want to give you that question.
Well, I mean, your thoughts on that would be interesting too, for sure. But yeah, I mean, so looking at only sentences with all of the arguments expressed, in that case, I would probably expect Russian to maybe be minimizing more, if only because of SEO being canonical, but then again, it's hard to say since it also has more flexible word order, especially like across genre, since what we're looking at here too is how genre affects that. So, right, so in that case, they might actually not be so different, or maybe Russian would minimize a bit, sure. Yeah, I'd have to think about it, but it's definitely an interesting question.
I think it's a good empirical question to investigate. There was another hand up. We have time for one more short question. Oh, there's Zoe. Okay, Zoe, why don't you go ahead?
Oh, thank you, Zavi. Alex, very cool. I've been thinking about the Bueno and Polinsky paper for quite some time, so it's good to see some actions on it. So I'm actually curious about argument drop. So what are the threshold of deciding that there was meant to be an argument in the first place? Because like we have similar phenomena, for instance, in Mandarin, but it's always a bit tricky to decide whether I was gonna say I in the first place, or I was going to say it, but I just made it in a speech. Does that make sense?
Yeah, so you're asking like what the criteria were?
Yeah.
Yeah, I mean, it's still preliminary, honestly, and I was sort of just doing it on my own sort of like instinct. Like if someone could hear the sentence out of context and like be like, wait, who did it? Or like they did it to what sort of thing? Like, so like with the transitive verb, it's like for ones where it was pretty clear. But I've been wanting to look into sort of like the criteria that are used in other works to determine that, you know, to get, I guess a more, what's the word, like more specific way of doing it. Cause right, it is basically just like, does it seem like there's something here that's not being expressed? Yes, okay, argument drop. Right, so that's definitely something to work on more.
Yeah, thank you.
Yeah.
Thank you so much, everybody. So we have our final half-hour break, and then definitely come back because Natalia Levchina, our final co-organizer, is going to give an amazing talk. And then we'll have 30 minutes for discussion at the very end.